I think, so when we think about biosphere, what do we mean by biosphere? And Rebecca Mann brought this up yesterday, that, there are these dependencies, and there is a kind of slippery slope that if you follow it, that you try to include all the dependencies of your metabolism, then you end up with the entire planet, right? And so I was going to go down that slippery slope, and let's see where it takes us. Unfortunately, we only have one example of a living planet, so there's only so much we can say on this question, but it's an important one for a number of issues. First, I'd like to say, that this is, at the Earth Life Science Institute, we've been around since 2012. And the Institute was founded on the idea that planet and life are intimately coupled and inseparable from each other, that these are one and the same thing, and that if you want to understand the origin and evolution of either, you have to consider both of them as a system. And so the idea and our strategy has been an open system exchange of ideas inspired by nature and how nature accomplished this feat. And we often say that the most important part of our institute's name is this, is this the pointer here? No, I don't know what that is. Any case, it's that dash between the earth and life. So a couple of key points I want to touch on in this talk. One is the idea of the living planet, that life is an open system. Oh, thanks. Life is an open system. So how do we go about drawing boundaries in an open system? This is a really interesting challenge, I think, to make. What we know about life is that the planet is the foundation, and it's a part of our metabolism. So when I look at mantle convection, plate tectonics, I see that as part of my body's metabolism, because my body doesn't have any boundaries that can be drawn around me. In fact, that it includes the entire planet. When you consider the deep time evolution of all the components that make a creature like myself. So let's zoom out. That's the first point that I want to discuss. Second is about planet individuality, whether we can expect any two planets to ever be quite the same, especially living planets, and that's the main thing. And I'll discuss that, why that could be a very difficult thing to answer. So, of course, we know life is an open system, right? There's an individual here, maybe, but it's porous. Things go in and things go out. All of the really essential things that make our bodies work are unstable. They decay, they need to be replaced, regenerated, replicated. This is, of course, an obvious point. What about this in deep time, if we think about the history of a planet, the history of all of life together, what happens to individuality in this open system idea? We do lose a lot of individuality, like if we look at the fossil record, these are crinoids. Some of you might recognize these fossils. This is a beautiful sample in the Kanagawa Museum of Natural History. Normally, when we find crinoids, we just find these little bits of the tentacles in the rock, but these are almost fully intact. But, where's the individuality? Do we think about a crinoid like that crinoid there is important crinoid? Now, there are counterexamples. There's Sue, it's a famous Tyrannosaurus Rex in a museum, in the Field Museum in Chicago. And it's famous because it's very well preserved, very, very nicely intact. And of course, they gave it a nice name, and so it became famous. So we can say that this Tyrannosaurus Rex has some individuality, at least in our public imagination. But when we go back in time, even on our family tree, I was explaining this to my children the other day, You have 2 parents, you have 4 grandparents, you have 8 great-grandparents, and 2 to the number of generations going back. And in deep time, what happens to individuality? What happens to our understanding of who we are and who the people who gave rise to us, our forebears? It's kind of lost. Like, what can I say about my great-great-great-great-grandparents? I don't know. I could probably find out their names if I can do a record search or something like that, but what do I really know about them? And there's a whole bunch of them. And all their personalities, what they cared about, what they did in their lives. We don't really know. I mean, individuality is something that matters to us in the moment, but over time it is lost. There is this entropy that takes place. And it's interesting to consider the temporal element of that. In a planetary context, of course, we understand that we live in a Earth system that, life is interacting with, of course, the atmosphere where we have to breathe. We need plants to photosynthesize from the sun. We have all sorts of cycles going on. This is known by everyone, so I won't belay that point. As we go back in time, though, as we consider the deep past, this is a logarithmic scale of time and a logarithmic scale of depth into the interior of the planet. For a planet like Earth, as we go back in time, we have to go deeper and deeper because the exchange of matter and energy extends deeper and deeper into the interior. So when we're thinking about longer time scales, then we're thinking about larger chunks of the planet. And of course, when we get into the history of life, we're talking about billions of years, then we're talking about depth scales that include the entire planet. And this is why I say that your metabolism involves the entire planet, because ultimately it does. We know that this is the ocean crust age. So the oldest ocean crust is almost 300 million years. It's a small fraction of the Earth's age. Most of it is quite a bit younger. And of course, we also understand that a lot of this is being subducted and returned into the interior. The circulation of rock between the interior of the planet and the surface is feeding life, right? This is a really important part of what is supplying autotrophic life in particular. I mean, we call it autotrophic life. And if you look up the definition of autotrophic life, it says it produces its own food. But it's actually not true that it produces its own food. That produces the food that autotrophic life feeds on. We have very small amounts of rock left over from the ancient Earth, right? The Archean rocks, these darker red, is actually a very small number of places on Earth where we can find these. Also Proterozoic. Most of the rocks that we see exposed on the surface are quite young. And this is an example that shows that the Earth's surface is constantly recycling itself. It's constantly changing. It's constantly exposing the surface to disequilibria, chemical disequilibria. Now, different planets have different paths. Now, this is a hypsogram, basically, not a hypsogram, a age curve. Now, it's estimated for Mars based on crater counting and things like that, and for Venus as well. And then here's for Earth, where it's more well-constrained. We see that actually a lot of Mars surface is quite old, right? So the majority of Mars surface is older than about 3.5 billion years, right? Whereas on the Earth, there's very, very little, almost a negligible fraction is older than 3.5 billion years. Most of the Earth's surface is quite young. It's way over here. Venus is thought to have a young surface. But of course, Venus is not a place where organic chemistry can take off and produce life. Mars, though, was very active and had a lot of overturning. So Mars was feeding the surface with energy, chemical energy, early in its history, but then it slowed down, it stopped, more or less. Whereas Earth has just continued to do that all through time. So let me skip to this. So in order to understand what's going on, we need to try and understand what is the circulation of material and matter and how this is driven by the cooling of the planet over time. There are many reasons why the interior of planets is hot. One of them is the release of gravitational potential energy as they accrete, right? A lot of that is converted into heat. It's a lot more heat than the planet needs to run. In fact, on the Earth, it's at least 40,000 Kelvin or so, which melts the planet. The planet gets rid of heat while it's in a molten state. When it freezes over, then it releases heat by solid state convection. In the mantle, the core stays mostly liquid, mostly molten, and then it's freezing from the middle outward, we think. So there's a whole science to how this works and how this is coupled to plate tectonics. And this is very important for understanding, for example, volatile cycles, carbon cycle, things like this, which intimately involves the planetary interior as part of its system. The other thing is that the atmosphere is going to lose hydrogen to space in particular, which is going to have a long-term oxidizing effect in the atmosphere. And this oxidizing effect in the atmosphere, combined with the more reduced state of the interior of the planet, then provides some nice chemical disequilibria when you can recycle material inside and outside. So this leads to this idea of a living planet. You know, if we take the idea that our metabolism involves the entire planet in deep time, and we just go down that slippery slope. Of course, we understand classic symbiosis. We had the nice examples of the honeybee and the flowering plants. At a larger scale, at a very coarse scale, we can think of autotrophic and heterotrophic life having a kind of large-scale symbiosis, and that's the biosphere, collective biosphere. But this is all connected to many different processes that are happening inside the planet. And this might be something we could call syngiosis, which is basically how the biosphere is coupled to and interacting with all these processes in the planet, which are then providing the energy and also regulating the environmental conditions necessary for life to persist. And so there's a lot of these things going on, and there's a lot of two-way and one-way interactions, but uplift, weathering, erosion, and those have feedbacks on things like plate tectonics and climate. And climate has feedbacks perhaps on plate tectonics and mantle convection. There's core convection, which produces a geodynamo, a magnetic field in the middle of the planet, which affects the atmosphere. And it stands off the solar winds. We have a lot of interesting things happening here. So this is a intimately coupled system that we have. So it leads to this idea of a planetary metabolism that, living things don't actually own or control their whole metabolism, that the metabolism involves the entire system. And there are interactions between all of these things, all of these major systems. And if you were to delete one of these were to be turned off, then the whole system would fundamentally change. And that's interesting, right? So you might end up with a planet which is dead, like Mars, for example. Here's a really wild example. This is one of our former PIs, Joe Kirschfink. He's wearing this funny hat. It measures brain waves. And what he was doing is actually sitting in a chamber which has a magnetic field that you can control and change the orientation. And so he was measuring how the brain waves change as you change the orientation of the magnetic field. And they were able to show that the human brain is sensitive to the orientation of the magnetic field. So we actually have a magnetic sense, a kind of magnetic compass. And some of us know how to use it or do use it. They were able to show that as well, which is very interesting. It's like a real sixth sense. But that only exists because there's a magnetic field generated in our core. This is what a simulation of the geodynamo looks like. These are magnetic field lines. It kind of looks like a big tango of spaghetti. But there's convection, which is fundamentally driving this process. And it's interesting that a process happening 3,000 kilometers beneath our feet is connected somehow to our brains. You know, we know that there are creatures which have, these are magnetite crystals, Fe3O4, and they grow these because it helps them to basically know magnetic field. Most places on the earth is more or less kind of vertical. So if they can orient themselves in the magnetic field, they can go up and down redox gradients, more light, more dark, whatever. They can regulate their environmental conditions. To produce these crystals, in fact, they need to have a very particular oxidation state, right? Magnetite is, right in the middle between wustite and hematite. So it's very interesting that life goes to the trouble to create these conditions that would produce these kind of crystals. Now this is an example, it's just a one-way coupling, right? The magnetic field is there, and so life is just using it, and it's adjusting to it. But what about going the other way? And this is where, as I mentioned yesterday, the Gaia hypothesis, this idea that, the original idea is that life takes charge of its environment. Basically, life takes control of the planet. In order to make the planet maintain conditions which are suitable for the persistence of life. Actually, this is generated by ChatGPT, and it's pretty funny. So it's the Biosphere, controlling the Earth, basically making the Earth a slave to its self, make good conditions for me, So this is what's been called maybe the strong Gaia hypothesis. And there's a teleological angle, which of course people have not accepted or did not find acceptable for the most part historically. And but yeah, this is a very one-way kind of thing, and we just don't see nature working this way, right? We don't see life exerting this kind of control on the planet. In fact, most people in the natural sciences see the things kind of go in the opposite way. So then there's weak Gaia, it's called. Weak Gaia is basically, okay, we'll take away all the teleological baggage. So, and then we'll just say, oh, this just kind of happens by circumstance, just spontaneously emerges that life is going to somehow have feedbacks or control the planet in a way that keeps things habitable. Maybe this is still a bit overblown for the weak Gaia hypothesis, but this is what ChatGPT will give you sometimes, which is pretty funny. Any case, the stability of the biosphere provided by planet life feedbacks is still a central theme in the Gaia. It's interesting though. It started off as something more like this, and then kind of has evolved into something more like this with time. In ELSI, as I mentioned, we consider planet life as a coupled system, and we don't really try to put one thing on, on an altar above another. It's basically, these are natural, spontaneous processes that are collaborating, and there's not any particular purpose or reason for them to happen in a certain way. So the idea is that, these are all deeply connected in deep space and time. And so this is a science of living planets. We think of living planets as opposed to life on a planet. And that's a very fundamentally different way of looking at the situation. So now I want to turn to this question, is a living planet really self-regulating? Do these self-regulating feedbacks exist? Is it a stable dynamical system such that if you perturb it, it's going to go back to where it was, to nice habitable conditions? Or are we just lucky? I don't know, after the last talk, it kind of looks like it could be either way, right? It's not really definitive. There's a lot of complicated things going on in the planetary system. So we don't actually know the answer to this question. We do have a successful example in the carbon cycle, which is, I think everybody is familiar with this concept, and how basically climate can be regulated by feedbacks in the carbon cycle. This has been well studied, and it's a really interesting case. If we look over a long period of time, we do have these changes. This is a plot of the percent of the present atmosphere level of oxygen with age. Age is going back in time to the right on this diagram. And so there's this great oxygenation event which happens, and perhaps a rise in oxygen. This is an older plot. There's a lot of newer estimates, but in any case, we know that the oxygen levels have varied quite a lot over time, and that this has given, presented some feedbacks on the atmosphere, and we think biology is involved. We don't know exactly how or exactly why or what the coupling is between biology and geology in these cases that is driving this, but it's definitely involved in what was going on. And there's this snowball Earth idea that if you draw down carbon dioxide and you produce a lot of oxygen, then the greenhouse effect is diminished and the planet cools down. As ice cover grows, more light is reflected back to space, so the radiation is not retained as heat. It's reflected back into space. And we have either continuous or discontinuous or periodic phases of snowball Earths, basically global glaciation events. And this certainly had to exert some sort of feedback on life. Did we get out of these things by luck? What was the feedback that got us out? I mean, one of the ideas is that continuous outgassing of CO2 from the interior of the Earth to the atmosphere, volcanic outgassing, kept producing a pressure to increase the greenhouse effect and raise the temperature again. So this is, that's a feedback going again from the Earth back to the atmosphere and onto the system that had been affected by life. Is this luck? Is it just right? Is it just the right amount to keep things from spiraling out of control? There's this idea, of course, of tipping points. Nathaniel mentioned this yesterday, but that a dynamical equilibrium might become unstable at some point, where a previously occupied state is no longer provides the feedbacks to keep things at balance, and then it tips and you end up in a new dynamical regime. So it's a dynamical phase transition that happens. I would argue that the advent of intelligent, I put quotes on intelligent life, arguably increases the risk of crossing tipping points as we have more power to change the environment. All right, so individuality of planets. Well, they all look kind of different, right? In our solar system, they're nice and pretty, and like everybody has their favorite planet, right? But what can we say about individuality beyond these kind of gross characteristics, their color, their size, their density, things like this, their distance from the star? You know, now this is a huge question that's just being raised. There's, I think, over 6,000 exoplanets that have been discovered at this point, and many more being discovered. Now, there's a resolution frontier, basically along this frontier here. Longer orbital periods have not been detected as much, except by imaging, which is becoming more plausible with the new missions that are being launched. Also, smaller masses are very difficult to detect. So these are still being filled in. This is still being, developed. But we see some kind of structure here, maybe emerging, but it's difficult to say. There's a lot of arguments over this, whether there's any sort of patterns of groups of planets and how they work. The target of planet science, I think, is to say, what is if we want to have a deterministic science, then we want to say, okay, if you form a planet this way out of these things, then you'll get this kind of planet, right? And so the planet is some function of its formation. The planet meaning its structure, differentiation, tectonics, volcanism, magnetism, biology, etc. All of the things that make a planet what it is. Formation, I mean the mass, the chemical composition, the accretion style rate, distance from host star, whether it has moons, what are its initial conditions, things like that. What is the function F? If we have this, if we can answer this question, I think we have the unified theory of planet science. Wouldn't that be nice? Then we can answer all the questions that I'm posing. But we don't know very fundamental things about F. Is it a deterministic function? We're still unsure about this. If planet 1 is made from formation 1, planet 2 from formation 2, does planet 1 equal planet 2 and formation 1 equals formation 2? This is still something that we struggle with, and we actually had a workshop here in ELSI some years ago where we brought a lot of people in planetary physics, and the conclusion was that the answer to this question is no. That nobody believed that planet evolution is deterministic, that attended that meeting anyways. It's not a scientific poll, but it's the sense of a lot of leaders in the community. Is F a rough or smooth function, right? So if you have planet 1 with some formation and planet 2 with some formation plus epsilon, are they anything like each other, right? We don't know this answer to this question. So this is really a tough thing, and this cuts to the point about planetary individuality, right? Do planets develop individual characteristics? Can we make sense of this, is it an invertible function? Oops, I hit the button. Sometimes Keynote takes a little time to... Is an invertible function? If we know the formation, can we get the formation from the planet? Can we invert this function? That would be nice. Basically, our planet's like snowflakes, and this is, cuts to the question of individuality at the planet scale. We have 4 terrestrial planets in our solar system. 2 of them have magnetic fields today. We think Mars did in the past, but not presently. Only one has surface water. Actually, 3 of them are volcanically active. Only one has plate tectonics, and of course, only one has abundant life. So there's a lot of diversity already in just these 4 bodies. So planets are different than stars, and when we look at exoplanets, most of the people doing the looking are astronomers, and they are, attached to this very successful example of stellar evolution. And there's the main sequence, and this is all very well understood. And most of the stars can be explained by this main sequence. This is the Hertzsprung-Russell diagram. You plot the temperature versus luminosity, and you can understand what the star is doing and where it is based on this. There's always been this hope that we could do the same thing for planets. But stars are, very different than planets. Stars are very high entropy production environments. There's a lot of heat being generated and dissipated. They have very short-term memory in terms of structures. These don't last very long, except for this internal stratification. That is a long-term memory, and that reflects the evolution of their fusion and their processes happening, nuclear processes happening in the interior. Terrestrial planets, on the other hand, have a lot of memory. They have a lot of things that are left behind. These rocks here on Mars are billions of years old. They've been kind of laying around like this for billions of years. You'll never see anything like that in a star, right? And we see lots of feedbacks between structures and planets and memory effects in planets and the biosphere and other things on the Earth and on Mars. So terrestrial planets are characterized by deep time memory. And so I would say, F is very likely to be a much more complicated function for terrestrial planets than for stars. I'm going to skip forward because the time is running short. But planetary systems, I think, develop in context as they grow and evolve. A planet's dynamical state is intimately convolved with its deep past. And, put an image of like an embryo here, and this is an embryo of a planet that's accreting and forming and being forged. But events that are happening as the planet's accreting and differentiated are going to affect its entire history of the future. So this is something that's really important. So how does a planet remember key events in the past in a manner that allows them to influence their future evolution? What's the mechanism? Well, one thing is just the idea of memory. You have some state A and some state B in a process which transforms state A into state B, and that process imprints itself somehow onto the subsequent state. Okay, and that's something that we can measure and see for ourselves. There's two kinds of memory, I think. One is that where this process is imprinted, and that's it. Nothing else happens. It tells us that the process occurred and gives us information about it. But then there's another kind of memory, which is active memory, which is that the process imprint actually influences the process. There's a feedback between the imprinting of the process on state B that then changes the rules of the game. And this is a very interesting thing that I think we need to make this distinction. And this is something that occurs across all natural processes. Whereas we have a pretty good idea about how information memory is transmitted biologically, geologically, we don't have this neat division of labor that biology has. Things are happening in a more messy, seeming way. But rocks store a tremendous amount of information. If they didn't, we wouldn't have a science of geology, right? So they do record past processes. So what are some examples of passive memory? Compatible trace element abundances or stable isotope variations. We can measure these and they tell us about the past, but those things don't influence the behavior of the geological materials. Whereas active memory would be changing major element abundances, which influences physical properties of the materials. Incompatible trace elements, which changes their behaviors. Unstable isotope variations, grain sizes, mixed versus unmixed phases. These actually can change the behavior of the system. This is one example where if you go to what used to be a plate boundary between two tectonic plates, this is in Northern California, and you look at what is it that makes a plate boundary? Like, why is the one plate sliding past another plate at this very focused zone of deformation? What is it that allows that to happen? And this is what you find. Basically, the rocks look away from the shear zone. The rocks look nice and crystalline and euhedral. As you get closer and closer to the shear zone, you see that they're broken down into finer and finer grains, and that the structure of the rock is fundamentally changed. And we know from solid state creep theory that this kind of rock is much, much weaker than this kind of rock. And that's how we can produce something like plate tectonics. This is Japan. We're here in Tokyo Bay. And there's the Pacific plate, the Philippine plate, and this is the North American plate. And they're all crashing together. And the Pacific plate and Philippine plate are colliding underneath our feet right now. So if you feel an earthquake while you're here, that's the reason why. But the point is that there's this focus zone of deformation that occurs where the plates are moving relative to each other. And that has a memory, an active memory. And the reason why plate tectonics occurs is because there is such a feedback. Probably I'm going to skip through this. So there's something called a subcritical dynamical state, which is basically one that is sustained only because the state already exists. That's an interesting nonlinearity that happens in planets, and actually it happens across nature, and we don't usually think about it. But plate tectonics can continue to manifest, can continue to operate, even if it's no longer possible to generate plate tectonics from scratch. And that's because the imprinting of the process onto the rocks makes it possible for plate tectonics to continue. It creates the weak zones, and those weak zones then provide the option for it to continue using those to operate plate tectonics. Geomagnetism is another example. Earth or any other planet could sustain dynamo action at its core, even if it's no longer capable of starting one from scratch. That's because the presence of a magnetic field helps to catalyze the regeneration of the magnetic field in the dynamo. And life. Earth could remain inhabited by living systems, even if it is no longer capable of starting life from scratch, right? Actually, once a planet has life, and life is diversified into all these different niches and exploited all these metabolic opportunities, it's actually not easy to kill it off, right? Life is pretty robust once it diversifies. So even if you couldn't start life from scratch, even if you don't have what's necessary, you could sustain life. So these are called subcritical states. And, the simplest example is friction, which allows us to walk or to pick up a laser pointer. If it didn't work this way, we wouldn't be able to do these things, right? That there's two dynamical states, at rest or sliding. And there's a coefficient of friction, which is basically you take the tangential force divided by the normal force. And there's a static friction and a dynamic friction. And we all know this. We all experience this every day. And so if you plot this on the horizontal axis, you have this dynamic and static limit. If you were to increase from 0, the tangential, the normal force, then you have this pre-critical stage. There's no sliding until you reach the static limit. If you go above that static limit, then you start sliding. You're in a supercritical regime. And as you increase the tangential force to normal force ratio, you slide faster. And then if you decrease it, you go back down. Here's the fun part. So if you continue decreasing it while you're sliding, you continue sliding. And so you're in this regime which we call subcritical. And you get to the dynamic limits, and then you stop sliding again. So it's kind of fun. So in this state here, where mu lies between the two limits, the answer to the question of whether it's sliding or not sliding is it's sliding if it's sliding, and it's not sliding if it's not sliding, which is kind of fun, right? And this is true of a lot of geological systems. And I'm going to actually go through the rest of this. There's other examples, but I think habitability is one of these types of systems where, you know, perhaps you have a pre-critical phase. You can increase, for example, metabolic power supply, and you can get to something like an originability threshold where you have the conditions needed to create life. But once you create life and it can diversify, it becomes robust, then you can take this down below the originability threshold and life can continue persisting. And then maybe there's a habitability threshold that you get to below which life would go extinct. So I look at planet evolution and all of these processes interacting with each other. You know, I try to look at them in a more stochastic way. Everything starts off with some nebula which condenses to form a central star, and then planets clump up from the disk that forms around the star. And as it goes through all these processes of becoming a planet, there's a kind of decision tree. It kind of goes one way or the other. And there's some probability maybe that it goes one way than another. There's probably nonlinear interactions between all of these things, but I've just drawn this as a simple tree. And if you go through all of these key moments, these decisions that are made on the formation of the planet, you'll get to eventually a distribution of outcomes. And then maybe some of these are not habitable. They're dead planets. Some of these might be good for simple life. And then some might actually be good for complex life. So I think this is one way of looking at it. And then maybe this is a way that we can approach this question of planetary individuality in a way that contextualizes all of these key events and puts the history of the planet into context. Okay, so I think I just want to kind of finish. So there's this thing, this topic, it keeps coming up, this Earth 2.0. We have to find Earth 2.0, I hear people say. And, you know, when I look at it from the point of view of what's the function F, and not knowing the answers to very fundamental questions, even if planetary evolution is deterministic or not, it's a bit disconcerting to hear this framed in this way, that like we're going to find another Earth that's like this one. Because Earth has actually managed to dodge a lot of bullets, escaped a lot of situations that would have shut down critical systems in the planet. We actually are not even sure how the Earth managed to overcome a lot of hurdles. For example, in recent years in ELSI, we discovered that the Earth's core has a very high thermal conductivity, and it loses its heat, which makes it very difficult to keep a dynamo going over 3.5 or more billion years of its history. So how to do that? We still don't know the answer to that question. How did plate tectonics even start? You go from a planet which is accreting and mostly molten to one that has plate tectonics. That's a huge change. We don't know the steps that happen between those. So there's a lot of things that's just the tip of the iceberg. But I think we won't find Earth 2.0. I think that there is no such thing. That's what I suspect. We'll find something very different than that. And I think it's analogous to, well, if you watch Star Trek, you know, then all of the intelligent life on the other planets, they all look kind of humanoid. They all have, you know, they walk on 2 legs and they have 2 eyes and mouths and noses and things like that. It's like, is that reasonable to expect is true of the universe? Intelligent life 2.0 is going to look like us, or ish. I don't think so. Anyways, food for thought. We don't really know, again, the answer to the question of planetary individuality because we only have one example. And wouldn't it be nice to have another to compare with? I think we're going to learn a lot in coming years to answer this question.